Hello everyone. So in this video, we are going to present our AI vision system, HoleSpot, for detecting potholes effectively using advanced computer vision techniques. This is part of the Smartathon hackathon competition, Theme 2. So here is an overview of our team members. We are a team of 4, all graduated from top UK universities with more than 3 years of research and industrial experience of state-of-the-art AI systems. And here is an overview of our system. Our system uses 2D object detection model and 3D reconstruction model to localize the potholes and predict their sizes. After the pothole detection, a fine-grained image classification model then classifies the severity of detected potholes based on their appearance. Using predicted appearance score and magnitude information of detected potholes, we can then evaluate the conditions of road segments and determine which potholes should be repaired immediately. Here are some of the benefits of our system. Our system and metrics are all well designed and applied high-performing computer vision models, which are easy to maintain for future data drift and model drift problems. We also designed a data dashboard for data visualization and decision making. Please refer to the link to try out our demo. So in this project, we deliver all the training, detection, and evaluation pipelines for each computer vision modules. We also designed a website for our data dashboard for presenting the important data for decision making. Here is the overview of our 2D detection model, which uses YOLO v5 algorithms because it's robust, fast, and lightweight. We split the dataset from Theme 1 pothole images into roughly 80 to 10 to 10 ratio for train, test, and validation. With the small size of training images, the model can achieve high performance for detection metrics with a precision of about 0.86, a recall of 0.67, and MAP of 0.514, which is suitable for industrial users. And here is our 2D object detection model. As we can see, here are some of the inference results, and nearly all the potholes are detected by our specific training model. And here is an overview of our 2D foreground extraction. Considering that we only care about the pavement condition in the foreground, we applied an efficient foreground extraction algorithm to eliminate the influence of the sky in each frame. This method lays on the assumption that sky pixels usually have small variance. We can notice from samples presented in the left side that our algorithm could efficiently mask sky in each frame. And subsequently, in order to localize potholes in each frame and estimate the frame condition of the whole scene, we should first provide the position of camera and then predict the depth information of each frame, which is also known as the trajectory estimation and the 3D geometry learning. We adopted the DiffNet published in BMVC 2022. We present the diagram and results of DiffNet on KT 2015 on the left side, from which we could learn its great performance on street datasets. So here are the results of our trajectory estimation. In this page, we can see, the axis represents the horizontal translation, and the y-axis denotes vertical translation. So here in this page, we'd like to present the results of geometry learning on both scene 1. The lighter the color is, the further the pixels from the camera. We could notice that our depth estimation algorithm could efficiently capture the location of different objects, including buildings and cars. So here is our pothole severity classification model. To classify the severity of potholes, we fine-tuned a pre-trained MobileNet V2 model. The advantage of this model is that it's lightweight with only 3.4 million parameters, so the training and inference processes are very fast. Moreover, despite its small size, its accuracy on image classification tasks is comparable or even higher than some of the models like VUG16. So we manually classified around 300 potholes from scene 1 into following 3 categories: mild, moderate, and severe. After splitting into train validation and test set, we augment the train set such that the model could acquire better generalization abilities. We trained one classifier for each severity category, and during inference, each model outputs the likelihood of a pothole to be in a certain category, and the pothole is then labeled with the category with the highest probability. So here are some of the inference results of Theme 2 potholes. And then we move on to the evaluation pipeline for our system. So our evaluation pipeline divides the road segment by 3D trajectory estimation, and then summarize all the pothole properties of 2D and 3D information, as shown in the workflow. We then sample the representative frames and calculating the scores by accumulating the pothole's severity score. And the representative video frames from each road segment are sampled based on the following criteria. First is the maximum number of detected potholes, the highest average score of detected potholes. The third is the largest bounding box areas of, and the final one is the highest average confidence scores of each detected pothole. We can calculate the score of each potholes, which are determined by adding the severity type of pothole and the weight of pothole volume. The severity type of pothole is determined by human visualization, evaluation, and image classification models predictions. The weight is increased by the higher accuracy of 3D reconstruction models. So here are some screenshots of our data dashboard. We display some useful information such as the total number of potholes detected and the percentage of each pothole severity. The summaries of road segments and their corresponding score can also be found on this page. We can also look at the dataset of all detected potholes with options to filter by fields such as severity, size, and the road segment for easy organization, search, and analysis. Finally, we can also present a summary of each individual scene using our custom metrics to provide an in-depth evaluation, hoping to aid the eventual repair decision and process. So in conclusion, we have developed a state-of-the-art computer vision models for robust and accurate pothole detections and evaluations, which are ready for production. We also proposed a novel road evaluation pipeline for evaluating the conditions of road segments effectively. We also designed a user-friendly dashboard for visualizing the data and determining which potholes are top priority. So that's all for our presentation, and thank you very much for your attention.